For separations of mixtures with microporous adsorbents such as metal organic frameworks and zeolites under conditions in which the occupancies within the pores are close to saturation, the separations are dominated by entropy effects that rely on differences in the saturation capacities. Microporous crystalline adsorbents such as MOFs and zeolites have a wide variety of pore dimensions, pore connectivities, and pore topologies. For example, AFI zeolite has one-dimensional channels whose width ranges from 7.3 angstrom to 8.4 angstrom. MAF X8 is a MOF with one-dimensional channels of 10 angstrom. Fe2BDP3 has triangular shaped channels. Modernite zeolite has one-dimensional channels of 7 angstrom in size. These are connected to side pockets that can accommodate molecules such as methane and carbon dioxide. These side pockets are acting as cul-de-sacs. Sodium X zeolite has cage diameters of approximately 11 angstrom separated by 7.4 angstrom windows. Chabazite zeolite has cages of 8.5 angstrom in size separated by 3.8 angstrom windows. LTA5A zeolite has 11 angstrom cages separated by narrow windows of about 4.3 angstrom. MFI zeolite consists of a set of intersecting channels, straight channels and zigzag channels, and the channel dimensions are approximately 5.5 angstrom. There are basically three different strategies that can be employed to separate mixtures using microporous crystalline adsorbents. We could explore differences in the binding strengths, and the binding strengths being dictated by van der Waals interactions, differences in polarizabilities, dipole moments, quadrupole moments, Coulombic interactions. For example, CO2 experiences Coulombic interactions with extra framework cations of zeolites or unsaturated metal sites in metal organic frameworks, and pi electron exchanges between guest molecules and the framework atoms. The second strategy relies on differences in the saturation capacities of the guest components, and essentially this is dictated by how efficiently the guest molecules pack inside channels. These separations are called entropic separations. The third strategy relies on choosing the pore dimension of the host material such that one of the guest constituents is effectively excluded. For example, this strategy is used for separation of methane from nitrogen in order to produce natural gas to meet the pipeline specifications. Such separations are basically kinetic in nature and not driven by adsorption equilibrium. The focus of this presentation is on exploiting entropy effects. Let us gain insights into entropy effects by examining the separation of mixtures of ethanol and 1-propanol using chabazite. Chabazite is an all-silica zeolite consisting of cages of 8.5 angstrom in size. Each cage is separated from the adjacent cage by windows with aperture of 3.8 angstrom. A total of 4 ethanol molecules can be accommodated within the cages of chabazite. For absorption of 1-propanol, a maximum of 2 1-propanol molecules can be accommodated within a cage. The unary isotherms for ethanol and 1-propanol are shown here. These unary isotherms were determined using configurational bias Monte Carlo simulations. For ethanol, shown by the green squares, a maximum loading of 4 molecules per cage is achieved at pressures or fugacities exceeding about 500 kilopascals. Indeed, you need to operate ethanol at conditions in which the bulk fluid is in the liquid phase in order to achieve the saturation capacity. 1-propanol, on the other hand, reaches a maximum saturation capacity of 2 molecules per cage. The binding strengths of 1-propanol and ethanol, as quantified by the ratio of the Henry coefficients, is 200, whereas the saturation capacities of ethanol to that of 1-propanol is 2. So we have competition between binding strengths and saturation capacities. Let us see how that plays out. Let us examine a set of experiments conducted by Denier and co-workers. These are breakthrough experiments for ethanol 1-propanol mixture in the liquid phase in a fixed bed tube packed with chabazite zeolite. The breakthrough curves are shown here. The blue triangles represent the breakthrough of 1-propanol, and this shows the breakthrough of ethanol. Remarkably, 1-propanol breaks through earlier than ethanol, indicating that the separations are selective to the smaller component ethanol. The x-axis in the breakthrough curves is the eluted volume expressed as milliliters. This hierarchy of breakthroughs is clearly not on the basis of the hierarchy of binding strengths. If that were the case, 1-propanol would remain more strongly adsorbed than and would break through later. So at face value, these breakthrough experiments indicate the manifestation of entropy effects. Let's see if that is true. In order to understand the breakthrough experiments of Denier that was presented in the previous slide, configurational bias Monte Carlo simulations were conducted to determine equilibrium between mixtures of 1-propanol and ethanol in chabazite zeolite. In these CBMC simulations, the partial fugacity of ethanol is taken to be equal to that of 1-propanol. The component loadings are plotted against the total fugacity in the bulk fluid phase F. The component loadings for 1-propanol are shown by the blue triangles here, and the loading for ethanol are shown by the green squares. We note that at very low bulk phase fugacities, the mixture adsorption equilibrium is in favor of 1-propanol that has the stronger binding with the framework atoms. The loading of 1-propanol reaches a value close to 2 molecules per kg that corresponds to the maximum allowable accommodation within each kg of chabazite. What is interesting is that if the bulk fugacity exceeds, say, about 1 megapascal, corresponding to a bulk liquid phase operation, the CBMC simulations show that the adsorbed phase contains a higher loading of ethanol than 1-propanol. In this graph, the adsorbed phase mole fraction of ethanol is plotted against the pore occupancy, where the pore occupancy is defined in this manner. We see that below a pore occupancy of about 0.7, the selectivity is in favor of 1-propanol that has the higher binding strength, whereas for occupancies greater than about 0.7, the selectivity is in favor of ethanol. The blue line here are calculations using the ideal adsorbed solution theory of Myers and Prausnitz, and the IAST is able to anticipate the selectivity reversal in favor of ethanol that occurs at pore occupancies larger than 0.7. Let us explain selectivity reversals and entropy effects for ethanol 1-propanol mixture adsorption in chabazite by considering the analog of a checkerboard. Each of the squares on the checkerboard represents a single adsorption site in chabazite zeolite. A single cage of chabazite can accommodate 4 green molecules of ethanol, or 2 1-propanol molecules indicated in blue. At very low occupancies, the component loadings are dictated by the relative binding strengths, and the adsorption is in favor of the longer 1-propanol guest molecule. The situation changes dramatically at higher occupancies because the vacant sites are more easily filled by ethanol. For example, this location can only be filled by ethanol. So is this location. So is this location. So is this location. for one propanol to be accommodated within Chabasite, it needs two adjacent adsorption sites to be vacant. Let us quantify the entropy effects by using the Boltzmann expression S equals K ln W, where K is the Boltzmann constant. This expression is also engraved on his tombstone in Vienna. We consider a binary mixture consisting of a Kamer and an Elmer. The Kamer is the ethanol guest, and the Elmer is the 1-propanol guest. Therefore, K equals 1 because it occupies one site, and 1-propanol, the blue 1-propanol, which is the Elmer, L is equal to 2. And on a checkerboard, N sub K represents the number of Kamers that occupy the adsorption sites, and NL represents number of Elmers. M is the total number. The Wahrscheinlichkeit, W, can be expressed as follows, where these factorials can be determined using the Stirling approximation. This is the Stirling approximation to determine the factorials, and the expression for the entropy can be used to determine the composition of the adsorbed phase that results in a maximum value for the entropy, and that is indicated by the black line. So the black line represents the composition of the adsorbed phase, that is the Kamer, that results in the maximum value for S. It's interesting to note that at 0 total occupancy, the adsorbed phase mole fraction is 0.5. In other words, for maximizing entropy, there is no preference between ethanol and 1-propanol. Whereas with increasing occupancy, for entropy maximization, the composition of the Kamer, which is ethanol, becomes increasingly in favor of the component with the higher saturation capacity. And at an occupancy of 1, the adsorbed phase contains only ethanol. The CBMC simulations for ethanol 1-propanol mixture adsorption are plotted here, because in the initial stages, the adsorption favors 1-propanol due to the stronger binding. So if we consider the minimum of the free energy, which is G equals H minus Ts, we combine the influences of binding effects and entropy effects and minimize the free energy, we get the blue line that is in excellent agreement with the Monte Carlo simulations. Incidentally, this blue line is determined by combining the entropy effects with the Boltzmann expression for S, with an expression for the enthalpy of adsorption determined from the binding strengths. These are not IAST calculations, but the resulting curve corresponds nearly with the IAST. The message to emerge from this is the following, that as the occupancy increases, the entropic contribution to the free energy becomes of increasing importance, and at an occupancy of unity, the adsorbed phase will contain ethanol almost exclusively. Let us strengthen the conclusions that have been drawn so far by considering the adsorption of mixtures of ethanol and 1-hexanol. The unary isotherms for 1-hexanol are shown here. The maximum loading per kg is 1. And here's a computational snapshot that shows that a maximum of 1-hexanol can be occupied within a kg. For a mixture of 1-hexanol and ethanol, the ratio of the saturation capacity is 4, whereas the ratio of binding strengths that favors 1-hexanol is 30,000. And configurational bias Monte Carlo simulations for the composition of ethanol in the adsorbed phase are shown by the red circles, and we note that beyond a certain pore occupancy, here about approximately 0.5, the mixture adsorption becomes in favor of ethanol. Experimental data, data A, for breakthroughs of mixtures of ethanol on 1-hexanol in a tube packed with Shaperside zeolite operating under liquid phase conditions are shown here. 1-hexanol is a component that breaks through significantly earlier than ethanol. This indicates that the most strongly adsorbed component is ethanol, the smaller molecule, rather than 1-hexanol that has the higher binding strength by a factor 30,000. These are the molecular simulations of the component loadings for 1-hexanol and ethanol in a mixture, and we see that if the bulk phase is in the liquid phase, the loading of ethanol is significantly higher than the loading of 1-hexanol. So the entropy effects in favor of ethanol are due to differences in saturation capacity that is in favor of ethanol by a factor 4 to 1. Molecular simulations for unary isotherms of water, methanol, ethanol, 1-propanol, and benzene in copper BTC are shown here, where the loading in moles per kilogram are plotted against the fugacity in the bulk phase. Consider the mixture of methanol and benzene. the ratio of saturation capacities is about 20:6 and favors the smaller methanol molecule. The composition of the adsorbed phase is plotted here as a function of the pore occupancy. With increasing pore occupancy, entropy effects favor the selective adsorption of methanol rather than benzene that has the higher adsorption strengths. The computational snapshots of the linear alkanes NC9, NC10, and NC25 in LTA5A zeolite are shown in these pictures. LTA5A zeolite consists of cages of 11 angstrom diameter separated from adjacent cages by 4.3 angstrom windows. Within a single cage, 2 of NC9 molecules can be accommodated, or 2 NC10 molecules, but for NC25, 1 molecule occupies 2 adjacent cages. Therefore, for mixtures of, say, NC10 and NC25, at pore occupancies close to saturation, entropy effects will favor the shorter NC10 molecule rather than the most strongly adsorbed NC25. We now demonstrate how entropy effects can be used to separate the isomers of hexane. Now, hexane isomers consist of normal hexane with an octane number of 30, 2-methylpentane with a research octane number of 74.5, 3-methylpentane with an octane number of 75.5, 2,2-dimethylbutane with an octane number of 94, and 2,3-dimethylbutane with an octane number of 105. For incorporation into the gasoline pool, the di-branched isomers 2,2-DMB and 2,3-DMB are the preferred components. And typically, in an alkane isomerization process for octane enhancement, the feed mixture is isomerized using a mordanite catalyst to produce a mixture of the hexane isomers that has to be separated into 2 fractions. The first fraction consisting of normal hexane, 2-methylpentane, and 3-methylpentane that is recycled back to the isomerization reactor, whereas the di-branched isomers 2,2-DMB and 2,3-DMB can be recovered for incorporation into the gasoline pool. The question is, which adsorbent to use and what is the separation mechanism? Let us examine the use of mordanite for separation of hexane isomers. Mordanite consists of 1D channels that are 7 angstrom in this direction and 6.5 angstrom in this direction. The 1D channels are connected to side pockets that have dimensions 4.8 and 3.4. The side pockets are unable to locate the hexane isomers. The hexane isomers are normally to be found along the straight 1D channels. And let's have a look at the animations for normal hexane conformations and 2,2-dimethylbutane. You will note that 2,2-dimethylbutane has a smaller footprint, and therefore at saturation it is possible to locate more of the 2,2-dimethylbutane within the 1D channels than normal hexane that has a longer footprint. In principle, it is possible, therefore, to separate the isomers of hexane exploiting on the entropy effects due to differences in the molecular footprints. By sampling several thousand conformations of each of the hexane isomers, it is possible to construct a probability distribution of the lengths of the footprints for normal hexane, 2-methylpentane, and 2,2-dimethylbutane. 2,2-dimethylbutane has the shortest footprint, say about 2.8 angstrom. 2-methylpentane has a footprint on average of 4.5 angstrom, and the normal hexane footprint on average is larger, which is about 5.5. Molecular simulations of the unary isotherms are shown here for normal hexane, 2-methylpentane, and 2,2-dimethylbutane, and you will note that at saturation the loading of 2,2-dimethylbutane is higher than that of 2-methylpentane, and the loading of 2-methylpentane is higher than that of normal hexane. The saturation loadings are the inverse of the footprints of the corresponding isomers. In order to demonstrate the exploitation of differences in molecular footprints to effect separations of hexane isomers, configurational bias Monte Carlo simulations were conducted for a binary mixture of normal hexane and 2,2-dimethylbutane, in which the partial fugacities of the two components are maintained equal to each other. The component loadings determined from CBMC simulations are plotted against the total mixture fugacity. We note that in the Henry regime, the component loadings are practically identical to each other, up to a fugacity of about 3 times 10 to the 4 pascals. But as the occupancy within the 1D channels of mordanite increases, the adsorption becomes increasingly in favor of the di-branched isomer at the expense of normal hexane that has a longer footprint and a lower packing efficiency within the 1D channels. The continuous solid lines are the IAST calculations of mixture adsorption using the unary isotherm data for the two components. A different way to explain entropy effects is to plot the adsorbed phase mole fraction of 2,2-DMB as a function of the mixture occupancy within the 12-ring 1D channels. The red circles represent the CFZ data calculated from the mixture adsorption equilibrium. The black line is the entropy maximization curve determined from the Boltzmann equation. S is equal to K ln W, where W is the Wahrscheinlichkeit, and the formula for which was described earlier in this presentation. We note that the maximum S curve qualitatively agrees with the Monte Carlo simulations of mixture adsorption equilibrium. The small differences between the maximum S curve and the CBMC data is due to the small differences in the binding energies. If we take the differences in the binding energies into account and determine the curve that describes the minimization of the free energy, that's the blue curve, we get nearly quantitative agreement between the minimum free energy curve and the mixture adsorption equilibrium determined from molecular simulations. The message to be drawn from this example is that the mixture adsorption equilibrium for hexane isomers in mordanite is almost entirely driven by entropy effects that are engendered by differences in molecular footprints. This is a computational snapshot of the conformations of normal hexane, 2,2-dimethyl butane, and 2-methyl pentane within the 12-ring channels of AFI zeolite that has dimensions of approximately 7.3 angstrom. Normal hexane has the longest footprint. The di-branched 2,2-DMB has the shortest footprint, and 2-methyl pentane has a footprint that is intermediate in length. Monte Carlo simulations for ternary mixtures of normal hexane, 2-methyl pentane, and 2,2-dimethyl butane are shown in this graph, and the hierarchy of loadings as post-saturation is approached is in decreasing order of the molecular footprint. And therefore, entropy effects can be exploited to separate hexane isomers using AFI zeolite. Hexane isomers can be separated using MFI zeolite by exploiting a different type of entropy effect. To illustrate this, let us consider the unary isotherm of normal hexane. Now, MFI zeolite consists of a set of straight channels and zigzag channels. The dimensions of 5.5 angstrom. Normal hexane is a linear molecule that can align along either the straight channels or the zigzag channels. This is the XZ view, looking at it from the top, and indeed they are zigzag in shape. They're also called sinusoidal channels. The length of a normal hexane molecule is commensurate with the distance between channel intersections. Per unit cell of MFI zeolite, there are 4 intersection points and a total of 8 normal hexane molecules can be accommodated within the MFI framework at saturation conditions. Monte Carlo simulations of the unary isotherm for 2-methylpentane in MFI zeolite are shown here. In contrast to normal hexane, a maximum of only 4 molecules per unit cell can be accommodated within the MFI framework at post-saturation conditions. This is because of the configurational penalty that is experienced by 2-methylpentane. It requires more legroom and it prefers to locate at the channel intersections, and an extra push is required to locate these 2MP molecules within the straight or zigzag channels, and therefore up to a pressure of 10 to the 4 pascals, the intersection sites are the preferred locations for 2-methylpentane. Configurational bias Monte Carlo simulations were carried out for binary mixtures of normal hexane and 2-methylpentane, where the partial fugacities of the components were maintained equal to each other. The red circles show the component loadings for normal hexane, and the green squares show the component loadings for 2-methylpentane. In the Henry regime of adsorption, the binding energies of the 2 hexane isomers are equal to each other. The component loadings beyond a total mixture fugacity of, say, 5 pascals becomes increasingly in favor of the linear isomer that packs more efficiently within the channel structure of MFI zeolite. Due to the configurational penalty experienced by 2-methylpentane that can only locate at the intersections, the component loadings progressively decrease as post-saturation is approached. Indeed, at post-saturation, the MFI framework is almost exclusively occupied by the linear isomer. Experimental data shown by the open circles and open squares are in quantitative agreement with the CBMC mixture simulation data. In this graph, the adsorbed phase mole fraction of normal hexane is plotted against the mixture occupancy. The CBMC simulation data are shown by the red circles, and these data are in good agreement with the curve that describes the maximum entropy, where S is calculated using the Boltzmann equation K, L, and W, where W is calculated using the statistics statistical model that was described earlier in this presentation. The message to emerge from this example is that the separation of hexane isomers in MFI zeolite is entirely due to entropy effects, because the differences in binding strengths are negligibly small. In the petrochemicals industry, the paraffins and naphthanes in straight-run naphtha are converted to the desired aromatics in a catalytic reformer. The products from the catalytic reformer are distilled to separate the benzene, toluene, and non-aromatics from the C8 and C9 aromatics that are recovered from the bottoms of the reformate splitter. The C8 and C9 aromatics are further separated in a xylene splitter, in which the C9 aromatics are removed from the bottom, and the C8 aromatics, consisting of orthoxylene, metaxylene, paraxylene, and ethylbenzene, are separated from the top and fed to an adsorption device that is called a simulated moving bed adsorber. There are two major product streams from an SMB adsorber. There's a raffinate, which contains orthoxylene, metaxylene, paraxylene, and ethylbenzene, and an extract phase that contains paraxylene, which is an essential feedstock for producing a wide variety of polymers, including polyethylene terephthalate and polybutylene terephthalate. Our focus here in this presentation is on the separation of orthoxylene, metaxylene, and paraxylene along with ethylbenzene to selectively produce an extract phase that contains paraxylene. Let us examine the separation of C8 aromatics. The boiling points of the four C8 aromatics, orthoxylene, metaxylene, paraxylene, and ethylbenzene, are very close to one another, and distillation separations are not feasible. However, there is a significant difference in the freezing points of the C8 aromatics. The component with the highest freezing point is paraxylene, and when the solution of C8 aromatics is cooled, the first crystals to come out of solution consist of paraxylene. This is because paraxylene stacks most efficiently to form crystals. Fractional crystallization is also a commercially viable technology for separating C8 aromatics. In this presentation, we consider the other alternative of separating the C8 aromatics by relying on entropy effects. Indeed, we shall look for adsorbents that rely on entropy effects to separate C8 aromatics. Now, paraxylene forms about 20% of the feed mixture that needs to be separated, and therefore we need adsorbents that selectively adsorb paraxylene from the mixture. Commercial units employ simulated moving bed adsorbers, and in most of the technologies that are offered currently, barium X zeolite is used as adsorbent. The picture here is just to demonstrate that the separation of C8 aromatics in an adsorption device requires us to recognize the differences in the packing efficiencies of the C8 aromatics within the crystalline framework. It is analogous to stacking books in a bookshelf. In current industrial practice, the adsorbent used in simulated moving beds is barium X zeolite that has the Fauger-site topology that consists of cages of approximately 11 angstrom size that are separated from adjacent cages by 7.4 angstrom windows. A very good description of the separation of xylene isomers using barium X zeolite is available in the thesis of Costa that is available online. And I use the information and the figures from this thesis to illustrate a few points regarding entropy effects. Let's consider first the adsorption of metaxylene in barium X. Within a single alpha cage, the location of the first two molecules of metaxylene is relatively easy. But the location of a third molecule within the alpha cage is energy demanding because it requires a reorientation of the meta isomer. The same is true for the ortho isomer. In contrast to metaxylene, the placement of the third molecule of paraxylene within BAX is not energy demanding because the longer paraxylene molecule can be located in the plane of the window and is stabilized by interactions with the oxygen atoms of the framework. There is no corresponding adsorption of metaxylene of all orthoxylene at the window sites possible. So, summarizing, the difference in the adsorption of meta-isomer and orthoisomer with the para-isomer is that with the para-isomer, the loading of 3 molecules per kg is more easily achieved than with the ortho and the meta-isomer, for which the location of the third molecule per kg is an energy demanding task. The thesis of Costa contains an interesting and important graph showing the selectivity of paraxylene with respect to metaxylene as a function of the total loading per alpha kg of faugisite zeolites. Blue represents barium X and the red symbols represent sodium X. For both these cation exchanged zeolites, the px to mx selectivity is the same up to a loading of 2 molecules per alpha kg. For barium X zeolite, the selectivity increases in favor of the para-isomer as the loading is increased beyond 2. This is because the placement of the third molecule of metaxylene is an energy demanding task, whereas the placement of the third molecule per alpha kg of paraxylene is relatively easy because the third molecule can be located in the plane of the windows. So the selectivity in favor of paraxylene is due to entropy effects. In a simulated moving bed adsorber, the feed of C8 Aromatics is in the liquid phase, and the essence of countercurrent contact between the liquid mixture and the solid adsorbent containing BAX zeolite is achieved by periodic switching of the inlet valves for the feed mixture, for the eluent that is commonly para-diethyl benzene, and the outlets of the raffinate phase and the extract phase containing essentially paraxylene. There are essentially 4 zones in the operation of an SMB adsorber. In zone 1, the adsorbent is regenerated. In zone 2, ortho, xylene, metaxylene, and ethylbenzene are desorbed. In zone 3, paraxylene is adsorbed selectively. And in zone 4, the element para-diethylbenzene is recovered and recycled back into the adsorber. Since the adsorption selectivity is in favor of paraxylene that is obtainable with barium X zeolite is of the order of 2, it is of industrial importance to examine whether alternative materials such as zeolites and MOFs offer improvements in paraxylene selectivity and uptake capacity. Let us examine a few candidate adsorbents, starting with AFI zeolite that consists of one-dimensional channels. The channel width is 7.3 angstrom at this position, and from groove to groove it's 8.4 angstrom. On examination of the molecular dimensions of orthoxylene, metaxylene, and paraxylene, it is possible to see that orthoxylene can be located vertically within the grooves in a face-to-face packing that results in footprints that are very small. On the other hand, metaxylene and paraxylene cannot be located vertically and occupy significantly longer footprints. Experimental data on the unary isotherms for orthoxylene, metaxylene, and paraxylene confirm that the saturation capacity for orthoxylene is significantly larger than for the para and meta isomers. Therefore, mixture adsorption is selective to orthoxylene, and this has been established in experimental data on transient breakthroughs. So it's possible to separate the xylene isomers using AFI zeolite, but the adsorption is orthoselective. Within the one-dimensional channels of MIL47, that is channels of 8.5 angstrom that are lozenge shaped, orthoxylene can be stacked because the dimensions are commensurate with the channel dimensions. Here are computational snapshots showing the commensurate stacking of orthoxylene within the 1D channel framework of MIL47. So it's possible to separate mixtures of xylenes, but the separation is not paraselective as we desire as alternative to barium X, but it's selective to orthoxylene. For optimal stacking of paraxylene within an adsorbent, we need channel dimensions which are about 10 angstrom so that paraxylenes can stack vertically. One such candidate is the MOF X8 that has 10 angstrom channels, and the computational snapshots show that the paraxylene molecules can stack face to face in a vertical manner. And this is also evident in this movie animation. Let us summarize the story that has emerged so far. Under post-saturation conditions, mixture adsorption favors the guest component that has a higher saturation capacity. If the feed mixture is in the liquid phase, post-saturation conditions are assured. In order to achieve high saturation capacities of the component we wish to selectively adsorb, we should choose materials that allow optimal packing of the guest component. The optimal packing could be, for example, face-to-face packing of crisps in a cylindrical container of Pringles, or face-to-face packing of pieces of chocolate, triangular in shape, in a Toblerone container. Within the triangular channels of Fe2BDP3, the stacking of 1,3,5-trichlorobenzene occurs in a face-to-face manner. This results in a very short footprint as compared to the footprints of 1,2,3-trichlorobenzene and 1,2,4-trichlorobenzene that cannot stack vertically. Therefore, these Toblerone-shaped channels structures may be employed to selectively adsorb 1,3,5 isomer from a mixture with 1,2,3 and 1,2,4 TCBs. The important takeaways from this presentation are summarized on the slide. Entropy effects manifest at high pore occupancies, and entropy effects compete with binding strengths. Often, the entropy effects are so strong that they can override and overturn the hierarchy of selectivities dictated by binding strengths. Typically, entropy effects manifest at pore occupancies larger than about 0.6 and favor the component that packs more efficiently and therefore has the higher saturation capacities. The saturation capacities of guest molecules depend on the cage capacity the size of the molecular footprints in 1D channels, and molecular configurations, whether the molecules are linear, branched, in general, entropy effects are correctly anticipated by the ideal adsorbed solution theory, but the Boltzmann equation for entropy provides a simple explanation of entropy effects on the basis of a metaphor using a checkerboard that represents the different binding sites. We've also championed the strategy of using porous materials where the pore dimensions and pore shape allow the optimum packing of the component that we desire to be preferentially adsorbed. Here is a list of publications that provide further information and background data on the exploitation of entropy effects in mixture separations using microporous crystalline adsorbents.